Hello. Today I have with me a vase full of Hershey's Kisses. And maybe you've seen a contest like that before, where you try to guess the number of candies in some kind of container. And this is the sort of thing that lends itself to empirical modeling. That's the topic of the next two sections of our video series, where we're going to analyze questions where there isn't really a theory-driven approach to take. It's more about observations. For example, this vase, if we want to know the volume of this vase, we really need to understand what is this curve right here. And there's a couple of different ways of approaching that, and one of them will be using polynomials. And so that's the topic of this section, is how do we find a polynomial, especially a higher order one than we saw in the last section, to help with our modeling. And so one thing that's worth being aware of is something called a Lagrange polynomial. And basically, it allows us to find the polynomial of degree no more than n that will fit n plus 1 distinct data points. So it turns out there's always an answer as long as the points are distinct, and by that we mean that the x values are never the same, which means a function is possible because it's going to pass that vertical line test. And notice the outline of this vase is exactly that sort of thing. If I assign the y value to the radius of each point on this vase, then because there's never a place where it has two different radii, then this would satisfy that condition. And so the question is, if I wanted to take some measurements and find those data points, what polynomial would fit them? And according to this formula, we can always find such a polynomial, even if we had 10, 20, 30 data points. Now, this is a little bit of a messy expression, so let's see it in action, and I think it'll make sense of why it works. So just to give us some data to work with, let's say we have x values of 1, 2, and 3, and y values of 4, 7, and negative 5. Now, of course, there's lots of ways to fit parabola, basically, through this data set. Notice it's 3 points, so n is 2, so that means degree of 2, so that's why it's a quadratic. But we want to do it in the spirit of the Lagrange polynomial. And basically that says the following, is I'm going to take the y value for the first term, so that would be 4, and then I'm going to multiply it by this ratio L sub I, which is a product. And notice the numerator is basically the product of terms of the form x minus the x values that aren't part of this first term. So x minus 2 and x minus 3. Because notice we've eliminated the first scenario here, the first point. And then the denominators is the same thing, but now we're plugging in the x value we skipped in for x. So that would be 1 minus 2 and 1 minus 3. So that is the first term of this polynomial where we put this product right here. Continuing on, y sub I for the second point would be 7. Once again, we have a product of x minus 1 and x minus 3. The x value we skipped was 2, so I'm going to do 2 minus 1 and 2 minus 3. And notice there's one more term left. I encourage you to write it down yourself first. Here's what I would write. Negative 5 for my y value, and then for my ratio, I have x minus 1 and x minus 2, because I'm skipping the third data point, which means since x is 3, I'm going to plug in 3 minus 1 and 3 minus 2. And notice this has the property that no matter which x value I plug in, I'm going to get the corresponding y value. For example, if I plugged in 2 for x, notice if I plug in 2 here, this entire term is 0, this entire term is 0, so they're both gone. And if I plug in 2 for x here, all of this is going to cancel out, and I'm going to be left with 7, which is what I wanted. And that would be true for any of the x values the way we built it. And notice each one of these is a product of two terms with a single x, so it's definitely degree 2. So this proves that it's possible to find such high order polynomials, again, even if I had a lot of data points, But from a practical point of view, this isn't very useful if one wanted to actually create such a polynomial. And so if it's a lower order polynomial, then we can use a spreadsheet like we've seen before. But we're more interested in high order polynomials. And that will be a topic for these next few videos where we'll do some examples. But some things to be on the lookout for. As with all modeling, there's always some pros and cons. And so here's some pitfalls to be aware of. Because when you have a lot of data points, you're more susceptible to a variety of things. One thing you're susceptible to more so is error in the data. All right, this is going to be a problem no matter how many data points you have, honestly, but sometimes a error in one point can heavily influence the rest of the polynomial. Another problem can be overfitting the data. We saw a little bit of this last time where having a really high order polynomial will get you a better R-squared value, but doesn't necessarily mean you're capturing the trend any better. So we'll have to be careful of that. With enough data points, you can start to see oscillation between points. So we'll be on the lookout for that. And the other thing that is generally true about empirical modeling, especially for something like the outline of a vase, is extrapolation that's meaningless. But anything involving a polynomial, extrapolation could be dangerous, and sometimes it just doesn't even make sense. So be aware of meaningless extrapolation. So if you do run into some of these things, then the solution may be smoothing your polynomial. In other words, you might want to intentionally choose a smaller order, a smaller degree. So it seems nice that if I have, say, 13 data points, I can find a polynomial of degree 12 and it will be a perfect fit, which notes from a perspective of SSE, I'm guaranteed an SSE of 0, right? Maybe that's worth mentioning on all these types of situations. But if that SSE of 0 just ends up causing some of these other pitfalls, then maybe we would rather sacrifice a little bit of error in the fit so we don't have some of these other problems. And so we'll think about that in the coming examples. So that's it for the overview. Check out the next video to see an example.